quality design. So what are the main features? How can you achieve that? Using diversification convergence, you can achieve it. And the three attributes for a good design is commodity. What are the three attributes we learn? Anyone? Anyone remember it? No, it is following. Firmness, commodity, and delight. So these things I already discussed in the previous class. And what is design? How can we achieve this? And how to convert the analysis model to design. Am I audible to you?
Yes, ma'am.
Anybody there?
Yes, ma'am.
Actually, I was taking class. Did you hear that? It was in mute, I think. Did you hear that? Okay, then I have to repeat again. In the previous class, we discussed about module 3 design concepts. In the design concepts, initially, I discussed about what is the principle, what are the practices, what are the concepts we need to follow. What is the definition of design engineering? What are the attributes for a quality design? Firmness, delight, and commodity. That what is it? We explain that part. And when it comes to how can we achieve the design, how can we achieve the design attributes through the diversification and convergence. And after that, I discussed about work products of design phase and how can we assess a model and what are the elements of analysis model and how can we convert this analysis model to the design model and how these phases are related. What is the input of what are the input for design models and what are the mapping means analysis model. Generally, analysis phase output is a problem statement. Means we are analyzing a problem statement. Then when it comes to the design phase, we are our output is models. Then it comes to the development phase, we have two outputs. Either we can create a prototype model or the actual solution or coding part. Then testing output as a tested solution. Solution, but just tested one. These are the mapping things I discussed. Then design process, I discussed characteristics of good design and guidelines of, and then quality attributes, verbs also discussed, functionality, usability, reliability, performance, supportability. So many things comes under supportability, testability, compatibility, configurability, extensibility, fault tolerance, modularity, reusability, robustness, security. So many things comes under supportability. Up to here, I think I completed up to here the quality attributes. Next, I'm going to discuss on design concepts. Design concepts, actually, these 9 points you need to learn. Abstraction, architecture, patterns, modularity, information hiding, functional independence, refinement, refactoring, and design classes. This provide a necessary framework for getting program right. Means these are the framework activities we need to follow to get a good design. Abstraction. What do you mean by abstraction? What do you mean by abstraction, anyone? Anybody is listening? Anyone is there? So raise your hands if anyone is listening. Okay, 6 participants are attending the last class. Okay, this is out of 35. Only 35 people joined out of 35. The remaining students actually they did not join. The people who joined also 36 out of 36. Only 6 means 30 students, they simply joined to get the attendance. So coming to design concepts, at least some students are there. So I'm talking for those students. So design concepts. One of the important design concept is abstraction. Abstraction means you already use the term in C++ or Java. That object-oriented programming, one of the main concepts we are using is abstraction. Means you are hiding something. The details you are hiding here. So irrelevant lower level details you can hide. That principle you can apply not only in the object-oriented programming, in many concepts, even the research, even the software engineering development, and not only in other, not only these projects, even hardware projects also. This is very important thing. That is, you need to give an abstraction, different abstraction. Means higher level to lower level abstraction means the details you can disclose, but not at a time. You can disclose one by one. So this is one of the important design concept. How can you disclose the details, and what is the need to hide the details? Why you're hiding the details? Okay, what we think, if we disclose all the details at a time, they will get more information. Then why should we hide the details? Any reason? For example, open the door. This is an example for a procedural abstraction. Open the door, because the verb open. But we never mention how to open the door. The procedures we simply ignore, because there is no need to explain that irrelevant details. It makes you more confused, right? So to avoid confusion, you can go for some hiding. Open the door. But how can you open the door? The steps, you just stand up from your place, you go to the door, just rotate your knob, rotate the doorknob. There is no need to explain those details. It gives more confusion. So avoid the unnecessary details. Procedures, if you hide, then you can call it as a procedural abstraction. If you hide the data, you can call it as a data abstraction. How can you hide the data? For example, door. Door, we are saying, but we hide the characteristics of the door, like attributes of the door you're hiding, like that main door, the thick door, big door. No need the blue colored or coffee brown colored door. No need to mention the characteristics. That to make you more confused. So you can avoid such type of details, either data or procedural details, but you can disclose whenever it needs. So that's why we are going for higher level and lower level abstraction. You can disclose the things in a procedural way, in one by one steps. One by one, you can disclose it, and you can come to a detailed. Then coming to architecture. What do you mean by architecture? Means overall structure. What is the structure of the system? That is the architecture of the system. You can relate these things with house construction. A house construction also following the same thing: planning, modeling. Modeling normally we won't do for a normal building, normal house. If you are going nowadays, 3D models are available. Okay, they will prepare a 3D model using some softwares, but otherwise before long back, actually, for very big complex big as a airport like things, when they're creating malls, shopping malls, they used to create a prototype model to explain to others. to get an idea before you're going to start the actual construction. That is a model, prototype model. Nowadays, the same thing they are doing using 3D softwares are there available. They will try. So the modeling also there. Then coming to architecture, architecture of means it's structure of your construction. So here what we are constructing, here we are constructing software. So the way in which the structure provides a conceptual integrity for a system means how the components, they are interconnected, how the data is used by those components that you will get from an architecture. Okay, we will discuss the architecture in the next part. The first part we are discussing about design. Next, second part discuss about the architectures. Then we will I will explain in detail. Then next is different architectural models are there. Structural models are there. Framework models are there. Dynamic models are there. Process models are there. Functional models are there. So different types of architecture models are there. So what do you mean by structural model means? It contains an organized collection of program components. Organized collection of program components which are organized in a particular way. That is called a structural model. Framework model means we identify the repeatable framework for similar type of applications. So that thing you can use reusability. It will increase the usability that you can use for other projects. Framework models you can use for. So we are creating a framework model and you can use the same model for the other softwares. Next is dynamic models. Dynamic models actually, which one is dynamic? Dynamic means behavioral diagrams, which are dynamic in nature. So behavioral aspects of the program structure is in the dynamic. Which one is changing? Some are stationary, some are changing. Then coming to process model, we design the technical process. Process model means always technical process. Functional models means represent the function done by the system, represent the functionality of the system. So architecture model also, not a single model cannot satisfy all the needs. So we can go for multiple models for architecture, for structure, for framework, for dynamic behavior, for process, for functions. So our model is different, design models are different according to the use. Next point is patterns. Patterns actually we are using for usage to increase the reusability. What is the reusability? Actually, some general solutions are there that we can use again and again for the applications. So patterns actually describe a particular design problem within specific context. So you have to, before you're going for patterns, you have to go for the domain analysis that we already learned in the last unit. Domain analysis, if you do the proper domain analysis, then only you could identify the reusability part. Means you divide in different modules, and the modules you can use for the reusable as a reusability. So describe the design structure will solve particular design problem within specific context. So you should identify the context. It's not applicable everywhere. So that's why we are saying you have to learn your system first. Then only you could do the domain analysis, and it provide a description that enable design to determine whether a pattern is applicable to the current work, whether the pattern can be reused, and whether the pattern can serve as a guide for developing similar patterns. So actually patterns, different types of patterns, some 27 types patterns, already built-in patterns are there for object-oriented programs, we can use it. And those patterns are reusable patterns. Where we can use that in Java, actually it's using, where we can use that particular pattern that you need to identify in your project. That part is called analysis. Domain you need to analyze. So 23 or 27, I don't remember exactly the number. 23 patterns, I think 23 patterns are there that we can learn, I think I'm not sure whether it is there or. So next is types of design patterns. Design patterns, architectural patterns are the design patterns are the idioms are. Are you listening? Are you listening? Anyone is listening? Okay, there are different types of design patterns. Architectural patterns means, okay, when you look at your, take an example like what our college or university campus. When it comes to the architectural pattern, what is it? It's a best, it's a basic level. It's an overview of this organization. That is a higher level strategy, means overall structure and how this is organized together. Means here components means what is a component here when it comes to the building, different departments. We can assume different departments of different components, how they are interconnecting each other. Okay. So this is the way that idea you will get when we consider the patterns, design patterns. Means suppose if you look at this campus from outside, you get an overall overview of this campus, like its shape. You may identify. Means I mean a plan only, not a front view. Front view you won't get a much idea, but we are always showing the plan. Plan means a top view. Then at least you could get some idea about the shape, where what are the blocks here, different IJ, okay, different blocks are there, so that you may get an idea. That is the overview. But when it comes to internally, medium level strategy, I can understand where the departments are and where the staff rooms, where the rooms are allotted, and what is the relationship between this. Anyway, in one block contains one department and the classes which supporting that department. So in this way, it is arranged that you will understand once you come to the next level strategy. That is design pattern. This patterns and medium level strategy is to solve the design problem. When it comes to software, that is the relationship between different components. That your component to component relationship we are discussing in the design pattern. Like component diagram is an example. In component diagram, actually, before you are the first one is deployment, then component. Component diagram, you will get an idea about what are the components, how they are relating each other. They are communicating each other, right? So then coming to the idioms, idioms are the lower level pattern, which are programming language specific. Means it varies from, it varies depends on the platform. Depends like for C, C++, Java, Python, every single language has its own guide, its own strategy, right? Its own principles. So idioms actually represent the lower level pattern. In such is very specific to the programming language, and it describes the implementation of software component, the method used for interaction among software. So means we are coming to the module. Module level means we are writing functions in that, and how those functions are communicating each other, and what is the relationship between those functions, like a small program. So first one is system, then system to component, and component to module. This is the way we are creating the patterns. Architectural patterns are the overview, higher level strategy, and it gives the define the subsystems, components, and their connections. Coming to design patterns, that is the second level strategy, means medium level component to component relationships we are explaining. And when it comes to idioms, we are coming to one inside one module. What are the functions and how they are related to each other? So more details are there in idioms. Then next is modularity. Modularity means I already said you the main principle of modularity is divide and conquer. Divide and conquer means, suppose if something is, we apply this divide and conquer rule not in software everywhere. The British ruled India applying this principle, right? Divide and conquer. They divided people into different groups. Then they are very weak. Then they started to attack. They started to attack, and we were conquered by the British. So this is the way. This is divide and conquer, dividing the people into categories to make them weak. The same principle we can apply here in software also. Like if you are going to prepare a complex software, you can divide the software into different modules. Each and every module are logically independent. Part. Okay, so what we are doing is we create one team, and the team members are divided in different groups, and each and every group is working on one particular module. So that is more easy. Then the modules we are integrating, then the integrated modules again join together, we create the system. So this is the track. So modularity, modules means it's separately named and addressable component. So when you create a module, it should be logically independent. Then only we can work separately. It should not means too much in the relationship between the modules. If it would be there, we could not work on independently. That's why create logically independent, independent standalone units. That is the modularity principle. So why we are going for this because of basic principle, divide and conquer. If you divide, you can conquer it. Okay, if you divide something, you can conquer it, even though it's complex. So this same divide and conquer principle you learn in data structure. In algorithm, sorting algorithm also used this divide and conquer principle, right? In which algorithm? Anyone? Anyone remember that algorithm? Are you listening me? Anybody is here? Anyone? Last year you learned the algorithms, right? Last year you learned some algorithms, data structure. In data structure, some sorting algorithms you learned using divide and conquer principle, right? Quicksort. Do you remember it? Quicksort, merge sort. A Strassen algorithm. Remember it? And even binary search also we are using, right? In searching algorithm, binary search. Yes, binary search also we are using because we created the mid we find the mid value, and above the mid value and below mid value again, we are doing the searching. So there also we are applying the divide and conquer principle. Anyone remember these things? Have you learned data structure? These students won't reply back. They are not replying anything. Either yes or no. Have you learned data structure last year? Have we learned searching and sorting algorithms?
Yes, ma'am.
Where we applied the divide and conquer rule. We applied in merge sort, quicksort, and binary search algorithms. Many places we applied the divide and conquer. So we divide into different groups, and we work on that particular group. After that, we are merging together. The merges or the name itself, it is there. Same principle we applied in Strassen algorithm. That is already covered in data structure, right? I don't know whether if people attended those classes. Online classes means many of the students are not there. So you may not remember the topic's name also. Then modularity. Is that really? Then modularity we can divide into modular decomposability, modular composability, modular understandability, modular continuity, modular protection. Based on different way we can divide. Decomposability means a systematic mechanism for decomposing the problem in subproblem. That is the general decomposability we are applying everywhere. All places where we are using this rule, you use the systematic decomposing into subproblems. That is the basic idea behind divide and conquer, and that is called modular decomposability. Modular composability. Then again, we are working on different modules, and at last we are integrating together. These components are assembled into a new system. That is composability, modular composability, modular decomposability. Then modular understandability. Means if you divide into different modules, that is more easily you can understand. You can easily understand that particular module than to a complex structure. So it increases the understandability. It will be easier to build and easier to change. Then modular continuity. Suppose if you make a small change in your system, in any updation, then instead of changing the entire program, you can work on the particular module which affect the requirement. So that is another advantage. So modular continuity is instead of changing the whole system or all the programs, you can make change only the modules which affected those requirements, the updated requirements. So you can work on that area. That is modular continuity. Modular protection. Modular protection means suppose if anything happens, any problematic condition occurs within module, it affects constraint within that module. That's why we are saying another property is very important. That is, we should reduce the coupling between the modules. So it won't transfer from one module to another. If suppose if any aberrant condition occurs, it will affect only that module. If it is standalone, if it is highly interconnected with other modules, means everything ripple effect will come. Means it starts from one module, but it's affect every single. So reduce the coupling. So that is the modular protection. So modular decomposability, modular composability, modular understandability, modular continuity, modular protection. These words you need to remember. Maybe 2 more questions we can expect from this modularity. So here, then definitely you will get it down. Like then it's better to go for maximum modules. Then we can reduce the complexity very much. Then finding a solution is very easy. Is it? Is it good? So there is another diagram I'll show you. This represents the number of modules, how it affect the software cost or effort. Here you could see if this is the number of modules. On x-axis shows the number of modules, and y-axis shows the cost or effort need for that many number of modules. So if the number of modules are less, if the number of modules are less, what will happen? To cost to integrate. Cost, this one is cost to integrate. This cost to integrate is very less. This is that arc. Integration cost is very less. Why? Because we have very less number of modules. So the number of modules are less, integration cost is less. But cost per module is high. Why? Because the module cost is high, means module is much complex. So the number of modules are less, then cost or effort we are taking to integrate is less, but per module cost is high because more people working, more period of time, even the time also need, because very complex they put it. But when it comes to the number of modules are high, if the number of modules are more, this is the x-axis, then cost per module cost is less. Why? Because modules are very simple, or it's not complex. So the per module cost is less. But what about the cost to integration? Cost for integration is high because we have so many modules. So integration cost is high. So both when the number of modules are less and number of modules are high, both are not good. One or another cost will be increased. So it's better to go for, you just plot the values, then you will get a curve like this, a hyperbolic curve you will get, and you take the middle of that. So almost in this area, you could see both are this point. This point actually, the cost per module and cost to integration, both are less. But that is almost in the middle. So the number of modules should be in between. In between, not too low, not too high. Instead of that, the number of modules will be almost in the middle, means the average of this. Then you will get a point which is region of minimum cost. Minimum cost to integrate and minimum cost to effort. Minimum cost or effort. So this is the point. This is called modularity versus software cost. Means it's not recommendable more number of modules, and it's not recommendable less number of modules too. Is it clear? Is it clear?
Yes, ma'am.
Any doubts on today's topic? I think many of the students are not listening.
Listening, ma'am.
Everybody is listening, everyone is listening, but even though I am asking, they're not responding.
In case if they don't know the answer, they'll not respond, ma'am. But everyone is listening, ma'am.
Listening, okay. So this is the modularity versus software cost diagram. If you have doubt, ask me. Modularity versus software cost. For everyone, this diagram is clear. This is an important diagram. So the number of modules, how many modules you can create for your project? The number of modules. That is, you have to plot. It depends on the project complexity. The number of modules you can, you will get a point which is almost in the average, in the middle of the number of means not too extreme, too high, too low, in between. Then you will get a region of minimum cost that represent this dotted curve. So minimum cost is this area. Next point is information hiding. Information hiding also same like what I done before, but different level of information hidings are there that I will discuss in next class. Functional independence, cohesion. This information hiding will explain. The way of hiding unnecessary detail. The design, before I said procedural, the abstraction is there. Means abstraction means we are disclosing, but one by one, not at a time. We are disclosing the details in different levels, like DFD 0, DFD 1, DFD 2, like that. We are disclosing all the details, but not in DFD 0 itself. Next year level, you are going for DFD 1. Then it depends on where you have to show the details. So the way of hiding unnecessary details is called information hiding. The designing of modules so that the algorithm and local data contained within them are inaccessible to other modules. It is inaccessible. When we are going information hiding, this concept we are using in object-oriented programming. How can you hide the unnecessary details? Unnecessary. How you gave the visibility? Visibility. What do you mean by visibility? So everyone just recollect that point. Visibility. How can you implement the information hiding? Anyway, you learn object-oriented programming. So I think people are very much tired and not listening and not responding. So we'll explain the next class the information hiding and cohesion. Information hiding versus functional independence. Functional independence. These different categories are there. The next is refinement, refactoring, design classes. Okay, tomorrow I can finish. Tomorrow I can finish this. The first part, the design models is next heading. Design models. Okay, the last one. So tomorrow I will discuss the remaining design concepts. Okay, we have time. So anyway, this is last class. I'm going to wind up. If you have doubt, ask me. Otherwise, I am leaving. Any doubts? Any doubts?
No, ma'am.
No doubt. No doubt. Okay then. Okay, then only 33 members are there out of 66. Okay, bye.